In the last video, we talked about entropy from a statistical perspective, and it was reasonably easy for us to count potential microstates for things like positions that molecules can have, and orientation that molecules can have. It can be a little more difficult for us to imagine the microstates associated with different energy levels that different particles in a sample can have. And for that reason, it is oftentimes helpful to provide a complementary perspective, which is the thermodynamic perspective on entropy, which looks at heat exchange and the relationship of heat transfer to entropy. So entropy, as we saw, was a state function. Heat and work, on the other hand, are path functions. It does, in fact, matter how you do the reaction in terms of how much work it may take to do the reaction or how much work can be released or obtained from a reaction. In this section of the notes, we're going to be particularly interested in special types of processes which follow what we call reversible paths. And so an example of one reversible path would be reversible heat transfer. If we have water and ice at exactly 0 degrees Celsius, then some of the water can freeze, but some of the ice can melt, and that is what we would describe as a reversible heat transfer. Similarly, if we're operating under conditions where the pressures of both the system and surroundings are almost exactly the same, then we're going to see the potential for reversible expansion of a gas. The gas can expand, but it can also contract under those conditions. We can't, of course, be exactly perfectly at equilibrium. If we are, then we observe dynamic equilibrium, but no net process. But if we deviate from equilibrium by just enough of a tiny hair to make the process favored in the forward direction, then we are dealing with something that is essentially a reversible function. When we are dealing with reversible functions, when we are dealing with, for example, reversible heat transfer, then we are able to calculate entropy changes for the process. And we do that by essentially taking the derivative of the reversible heat change with time. However, if we are operating at a constant temperature, if we are dealing with an isothermal process, then we can skip the calculus for now, and we can simplify that equation to say that we are dealing with entropy change is equal to reversible heat transfer divided by temperature. So let's look at an example of that. We have water at 0 degrees Celsius. We know that water is able to freeze at 0 degrees Celsius. We can first ask ourselves if we expect the entropy change to be positive or negative based on what we understand about microstates. In this case, we are talking about ice melting, so going from solid water to liquid water, and the molar heat of fusion, the heat of melting for that process, if it's done at constant pressure, will be the same as the enthalpy change for that, is equal to 6,007 joules per mole. Remember that at constant pressure, Q is by definition enthalpy. So this reaction here, we take solid water and we melt it to liquid water. Do we expect that that corresponds to an increase in microstates or a decrease in microstates, assuming that we're operating at the same temperature? Well, I would expect it to correspond to an increase in the number of possible microstates, because when you have solid water in ice, you have a crystalline network, and there is a more restricted set of positions that the water molecules can occupy, and there is a more restricted set of orientations. So I would say that the solid ice is more ordered and the liquid water is more disordered, And therefore, we're seeing an increase in disorder. And therefore, we are expecting a positive entropy change, an increase in disorder. Now, this is the point at which I should probably mention the word random, because an awful lot of sources like to use the term random when discussing entropy. You will find that it is best to avoid the use of the word random in this course because it drives our local physical chemist absolutely insane, because it isn't as accurate a term as talking about disorder. Disorder has meaning. Random kind of doesn't. So moving on to our calculations, if we want to calculate the entropy change for ice melting at 0 degrees Celsius, that's the reaction as I wrote it at the top of the page, then we know that our entropy change for this process will be equal to the reversible heat change divided by the temperature, which, as we already noted above, as long as we're operating at constant pressure, is the same thing as the enthalpy change divided by the temperature. And so we have 6,007 joules per mole divided by 0 degrees Celsius, which is 273.15 Kelvin. And you must always convert your temperatures to Kelvin when doing any sort of thermodynamic calculations. And so throw those numbers into a calculator and I get 21.99 joules per mole Kelvin. I have 4 significant figures in my heat change, so I have 4 significant figures in my answer. The next part of the question asks us to calculate the entropy change for water freezing at 0 degrees Celsius. So now we're looking at going from liquid water to solid water. Well, if it requires the input of 6,007 joules per mole of heat to melt solid water to liquid, then we will be releasing 6,007 joules per mole when we solidify a mole of water. And so when we reverse the process, we reverse the sign on the enthalpy change, and for that matter on the entropy change, and for that matter on the free energy change. Repeat the calculation here. You're going to see we're going to get the same numerical value, but now with a negative sign in front, because now our reversible heat change divided by temperature, which, because we're operating at constant pressure, is the same as enthalpy change divided by temperature, is equal to negative 6,007 joules per mole divided by 273.15 Kelvin, which is negative 21.99 joules per mole Kelvin. And so melting water has a positive entropy change associated with it. Freezing water has a negative entropy change associated with it.